So now it's my pleasure to welcome Professor Andy Baker to present the Clark Memorial Lecture as part of the award of the 2022 Clark Medal. His topic, Caves as Observatories of Groundwater Recharge. Andy is an international authority in cave science, hydrology and geochemistry, especially as it pertains to our understanding of karsts, KRSTSs. They're complex underground systems formed when rocks dissolve and are characterised by sinkholes, caves and speleotherms or stalagmites. And I take my hat off to you, Andy, for daring to go into caves. His research focuses on the intersections between geology and water, from caves to aquifers. Using stalagmites, and he can reconstruct past climate, past groundwater recharge, and past fire history. He characterises organic matter in natural and human environments, from groundwater to drinking water, using isotopic and geochemical techniques. He has published more than 260 internationally refereed papers, including highly cited publications in Nature, Nature Communications and Science. Before Andy speaks, I should tell you a little bit about William Brownright Clark. Anglican clergyman, an expert amateur geologist, and present Andy with this, the Clark Medal. Clark arrived in New South Wales in 1839 to take up a chaplaincy at the age of 52. By that time, he already had a considerable cultural and scientific reputation in England and had been elected to the prestigious Geological Society of London. In Sydney, he served briefly in St Peter's Parish in Campbelltown and as headmaster of the King's School in Parramatta. In August 1846, he moved to St Thomas's Church in North Sydney, where he remained as its first rector until his retirement 25 years later. A stained glass window in that church memorialises his service, and if anyone of you has a chance to go into that church in North Sydney, it is beautiful, as is the stained glass. In addition to his ministry, Clark pursued wide-ranging geological fieldwork in Australia. He confirmed previous reports of gold deposits west of the Blue Mountains. He discovered diamonds, Silurian period rocks from more than 400 million years ago, and the age of the coal-bearing rocks in New South Wales. He also had a long-standing interest in zoology and paleontology. Among other things, he discovered fossils in Queensland of the extinct giant moa, a flightless bird. He also played a very important role in the Royal Society of New South Wales. He was its longest-serving vice president and delivered the vice presidential address to the Society's first annual meeting under the name Royal, after Queen Victoria granted royal assent. At that time, the Society's patron took the title of president, so the vice president was the working horse of the Society's council. You'll find Clark's 1867 address in the Society's journal, which, as most of you know, has been digitised and is available on our website. After his death in 1878, the Society inaugurated the Clark Medal and the Clark Memorial Lecture. They were initially separate, but now are combined into one award. The Clark Medal makes the Society the first colonial society in Australia to reward scientific achievement in this way. The first medal was awarded in 1878 to Professor Richard Owen of the British Museum, famous for his studies of Australian vertebrate fossils. In 1879, it was awarded to George Bentham of the Royal Botanic Gardens of Kew he made a major contribution to the study of Australian flora. And in 1880, it was awarded to Thomas Henry Huxley, the third recipient of the Royal School of Mines, London, for his contributions to the knowledge of the natural history of Australia. And fortuitously, yesterday, I picked up in the mail from Gail Newton, a former senior curator of photography at the National Gallery of Australia, the original letter from Thomas Huxley that she found in a box, written on the 11th of November 1881, accepting his Clark Medal. This will go into the Society's archives. I made a copy of it if anyone's interested in reading it. This isn't the original. The first class lecture was delivered in 1903 by geologist and Antarctic explorer Sir Edgeworth David. His topic was the life and work of Clark. Another Antarctic explorer, Sir Douglas Mawson, delivered the lecture in 1948. Today, the combined Clark Medal and lecture is awarded for distinguished research in the natural sciences conducted in Australia and its territories. The fields of geology, botany and zoology have been rotated up until 2022. Andy Baker, the 2022 award winner, receives it for the field of geology. So congratulations, Andy. Where are you? You join an illustrious lineage of Clark medalists, and I'm delighted to present you with the Clark Medal.
Lovely, thank you very much. Okay, well, so thank you all very much. It's a great honour. I hope to make the medalists before me proud by giving a presentation tonight on something about all these aspects of my research over the last 10 years or so, which is using caves as observatories of groundwater recharge. I'm going to try and link the groundwater world with this use of caves and cave exploring. The picture here is from Wellington Caves in the central west of New South Wales, and I'm going to give examples through the presentation this evening from New South Wales, given the medal and the location. So the outline I'd like to give then is I'm going to talk a bit about groundwater and how groundwater is recharged. Some of you may be groundwater people, you might have boreholes as a water supply, and for some of you it might be quite invisible. So I'm going to talk about groundwater and why it's important. I'm going to then talk about why caves could be used as observatories of groundwater recharge, give some New South Wales examples, and at the end I'm going to talk about the latest venture we're working on, which is this very grandly titled National Groundwater Recharge Observing System, which was funded by the Research Council a couple of years ago. We're not national yet, but that's got us the funding. So we're in Southeast Australia at the moment and trying to expand. And we're using more than just caves. We're using any underground space that we can find. So after the presentation, if you know of any interesting underground spaces that aren't caves, I'd be very interested to know and trying to expand our network. Before I start, this is not my work, it's work of many people. So lots of thank yous here. I'm going to go very, very briefly through them. First of all, the groundwater colleagues at UNSW, where I work. Pauline Treble, who's a research scientist at ANSTO out at Lucas Heights, invited me to join her team when I immigrated 13 or 14 years ago, and we've collaborated ever since. We had generous funding from the research councils and the federal government National Collaborative Research Infrastructure Scheme. My caving buddies are the Kempsey Speleological Society, who go up into the upper Macleay, and they've been actually running some of this data collection with me, and they've been amazing. I've also got to thank the staff of some of the commercial caves, so Dubbo Regional Council, which is Wellington Caves, and the National Parks team at Urangarelli. There's some intellectual ideas in here, not just mine, so Andreas Hartmann, collaborator at the University of Dresden, Mark Cuthbert, who's a groundwater person at Cardiff, and Andrea Cichetto at UNSW. And then finally, there's a team of people in this observing system that you'll see their photos later on in the presentation. So first of all then, why is anyone interested in groundwater? And I've got this slide. This is the promo slide that I would often give for going for funding, for example, for research councils or other bodies. But the context here is if you think about our First Nations people, how do you become the oldest living civilization continuously on one continent without groundwater? If you think about you need water to survive. Many of the river systems here are temporary and they're saline. So to survive and flourish here for 60,000 years before settlers arrived means that you need to have an understanding of groundwater and permanent and fresh groundwater resources. And then when Europeans arrived, and at the time, as I've just heard of early geology pioneers going across the Blue Mountains, the agricultural development across the mountains came because we could put windmills in like this one, which is out at the University Research Station out at Wellington, to tap the groundwater. And without that, the Europeans that arrived and settled couldn't then go and develop the inland area for agriculture because they needed the groundwater to survive and actually to flourish, because Australia, as we know, is a water-limited continent. It doesn't have enough rainfall. So the sort of figures I've used in the past, we need to update this figure. So more than 10 years ago, Deloitte were commissioned to work out the value of groundwater to Australian economy, and 10 years ago it was worth 6.8 billion GDP equivalent to the whole economy. So that's agriculture, mining, industry, all the sectors there. At the end of the last drought, the New South Wales government invested $3 billion just to try and find more water for drought relief. $3 billion over a couple of years. And these days, the figure's a bit wobbly, but up to 70% of irrigation water across the whole of the Murray-Darling Basin is dependent on groundwater. So this is a fundamental resource to our economy and our society. So we need to understand more about it. So if you're not sure, or haven't thought about what is groundwater, it's the water that's held in the pores and the spaces in the rocks. Underneath us here will be Sydney sandstone, Jurassic Age Hawkesbury sandstone. And everywhere around the city you'll see the same rocks. If you've not thought about the geology of the city, if you're not a geology background, you'll see the rocks. They're sandstone, sand grains, held together with some pore space between them. And then you'll see lots of fractures vertically, which is tectonics that have occurred since the Jurassic 200 million years ago. And there'll be horizontal strata, which will be different architectural units of the large river that formed the sandstone of the Jurassic that's here in Sydney. And we think that the river that deposited the Sydney sandstone 200 million years ago would be the size of the Brahmaputra today. So imagine a huge river meandering across a huge floodplain, depositing these big sandy sediments. That's all then been turned to rock, lithified over 200 million years. It's full of fractures, these vertical pathways, and horizontal bedding planes. And the water can percolate through the pores, or it can percolate down through the fractures. So in this example here on the right-hand side, we have fracture flow. We have fracture flow in the Sydney sandstone. And we have porous flow. This one says gravel, but actually be through the sand grains. And it's rained quite a lot the last few days. And if you go and drive around the city or the freeways, or you look at, or depending on the train line that you take, and you look at where the water's coming out through the sandstone, you'll find it's coming out through horizontal bedding planes and units between the sandstones. So the water percolates down through the sandstone, finds a fracture, often the horizontal units, and then it flows out sideways, and you'll see it pouring out the side on the Pacific Highway, for example, and you'll see it percolating through some of these layers elsewhere. So what is groundwater then? So groundwater is this hidden resource. It's underneath our feet at the moment. It makes up 99% of the liquid fresh water on the planet, so that's a bit of a cheat, isn't it? So I've removed all the ocean water and I've removed all the ice caps. But in terms of accessible water, water that you can use, 99% of the fresh water is actually groundwater. And for many people, it's a hidden resource. So a lot of the time when I'm teaching at UNSW, I'm teaching about groundwater to try and encourage our current students to actually understand this resource. It comes from precipitation. So rainfall that falls on the land surface, percolates down through the soil, and then reaches the groundwater. It can also come from rivers and lakes, which are leaky from the bottom, and it leaks into the groundwater system. And some of the terminology you might see around the place, for example, you'll see the water table, which is the boundary between the saturated groundwater, and then the unsaturated zone, which will be the soil and the area above that. And I'm going to talk about a few of these things in the examples as I go through. Now, I've thrown in two technical slides here for those that are interested. I'm going to talk about groundwater recharge quite a lot, which is the replenishment of the groundwater. It's worth all these billions of dollars to the Australian economy, but how well do we know how much of the rain gets into the groundwater? And I'm going to be asking you in a few minutes' time about how much rainfall you think is needed to actually get the water to reach the groundwater. So I'll be asking some questions about that in a minute. So there's a whole bunch of different ways the water can get there. I'll just put this slide in because some of these terms will come around again. So we have the rainfall coming into the surface. It will infiltrate into the soil, but we'll lose some. This ET thing is everywhere. This ET is evapotranspiration. It's the water lost by evaporation and transpiration. So it's trees and plants using the water, but also the direct heating of the Earth's surface losing the water there. And it appears everywhere, and it's really hard to measure. So we have rainfall falling on the surface, some of it's evaporated, some of it's transpired, some of it reaches the soil, starts head down towards the groundwater as direct recharge, but it can still lose some because the tree roots from our eucalypts can go down tens of meters. So even if the water's happily going down towards the groundwater, we can start to lose it again. So that's direct recharge. Or you might have, like we might have seen the last few days of the weekend, water reaching the surface, it's so wet that you get runoff, so you get rivers forming and it flows over the land. We're going to lose some again from evapotranspiration, and eventually it will maybe reach a topographic low, a depression or a joint, infiltrate down into the soil again. We'll lose some more from it by evapotranspiration, and then finally we might get something going to the groundwater, which is this focused recharge. And then the final example is where we have that water reaching the rivers, where again, yes, we get more evapotranspiration, and the rivers or lakes might leak, and again we might lose some more while it's leaking, and we have this indirect recharge. So we have all these three different processes. I'm going to be spending most of my time in here, in the caves, in this zone here. I'm not going to go into a cave that's underneath a leaky river or a lake. I don't know any, but I'll be very interested to find some. So the question then, the core question is, if we're so dependent on the groundwater, how much rainfall is needed? Now we have some technical techniques that we use. This is the only really technical slide of the whole presentation, just for those that are interested. There are three techniques I'm going to highlight from here. They are all so wobbly in terms of their quantification that groundwater scientists and researchers and engineers will talk about the term recharge estimation. They're always estimates because they are so imprecise. So how do we do it? Traditionally, what we might do, if you've got a borehole, what we might do is use this approach which is called chloride mass balance. This approach relies on the fact that all the rain that falls on the land surface won't just be rain, there'll be a little bit of salt in it. So imagine the rainfall falling in your garden or somewhere that you know, and then that rain evaporates up. So the water evaporates away by evapotranspiration, but the salts accumulate over time. And eventually there'll be a rain event that flushes that salty water down into the groundwater. And then you have that salty water which you can measure. So you can measure the amount of salt in terms of chlorine in the groundwater, compare it to how much is in rainfall, and measure how much it's been up concentrated. And the more concentrated it is, the less recharge there's been. There's more evaporation that's taking place in the soil. And so you can get these very nice maps, which are annual averages of groundwater recharge, but it has all these assumptions. It assumes that the only source of salt is in the rainfall, that there's absolutely no salt in the soil, there's absolutely no salt in the geology, which is all incorrect, and that all of the water goes directly through the soil and doesn't go off by runoff and doesn't go anywhere else. So we get a figure, but it's quite wobbly. Or we can use the water table fluctuation method, this one here, where you put a water level logger in the borehole and you watch the water go up and down, and if you know how much that water is actually then stored in the rock and transmitted through, which is this very wobbly term here, the specific yield, which we don't know, but if we knew it, you could just measure the height here, multiply by the yield, and that's your water table. Then that's your groundwater recharge, that's the amount in a height equivalent. But again, there's all these unknowns. First of all, you've got to be able to measure this here. And that's not very precise to go and do. This might just be a few centimetres to go and to try and measure. But also, the water's got to actually arrive faster than it's leaving the system, otherwise it won't go up at all. We don't know this term. And it has to be a purely untouched system where you've got your borehole. So no abstraction, no irrigation, no pumping, no anything, no chance. Because anyone's got a borehole, they're using it for something. They're not going to be sitting there. So that doesn't work very much. Or you can use water isotopes, which is a technique which works in some regions of the world, where the rainfall happens to have a different chemical composition. It has different isotopic composition of the oxygen and the hydrogen, which depends on the rainfall amount. And in the tropical regions, what you find is that as the rain gets more intense, the heavier isotopes of oxygen and hydrogen get rained out first. The lighter ones are left in the rain, and so we can relate the isotopic composition, which is these two terms here, to the rainfall intensity. So on this very complicated plot here from a group in ANSTO, we have a bunch of data for the groundwater, a bunch of data here for the rainfall, and where the two lines cross is the amount of rainfall per month where the groundwater is actually recharged. And so for this figure, it comes up with a figure of 150 to 200 millimetres a month of rainfall is needed to recharge the groundwater, plus or minus quite a lot. For this location here, and that's a mangrove mountain, and I've included that because I live on the Central Coast, and so that's one of the local regions to me. And there's some boreholes here which are monitoring boreholes, so they're not being pumped for anything else. They're there because of the Newcastle disease outbreak from many, many years ago, and they've had to put in lots of monitoring. So there's lots of boreholes around Mangrove Mountain because there's a pollution plume that's publicly readable on the New South Wales government website, which may or may not be heading towards the drinking water supply for the Central Coast. So they're monitoring it very carefully and make sure that if they need to do any remediation, that they can. So why then crawl around in caves, do all this wriggling around, to use caves as observatories of groundwater recharge? I've tried to make the case that these other techniques are estimates at best. Often they're annual averages, sometimes they're monthly averages. You really struggle to see anything that relates to individual rainfall events, which means it's very hard to relate it to things like climate. So in the cave, in here, we are situated in the unsaturated zone. We're above the water table, in the unsaturated zone, and the water can percolate down through pores or fractures into the subsurface. And we're directly observing the water percolating from the surface to the subsurface. So we're observing potential recharge. We probably know where the water's come from the soil, so we can get some idea of the process. Depending on where we are in the subsurface, we can have a good idea whether it is going to be actual recharge. So if we're monitoring down here, it's going to reach the water table. If it's up here, maybe not. Maybe a gum tree will still take it. And if we can see the water percolating down through the cave, and we can see that and collect it or measure it real time, and we can compare it to the rainfall that's occurred on the surface for the weather stations and the data from the Bureau of Meteorology, then the premise is that we can actually work out how much rainfall is needed to generate groundwater recharge at an event scale. And this is something called the rainfall recharge threshold. And that's what we've been doing. So we started this off about 10 years ago. Putting loggers into caves, trying to collect enough data. Now, so here's the question. I was going to ask you a question. So how much rainfall do you think is needed to generate groundwater recharge? How much rainfall in a day? And to give you some ideas, I generated this slide, but I submitted this to the Society a week ago. So, and then of course it poured in rain last weekend. So this is correct as of the end of last month. So I've taken the nearest weather data from here, which is Sydney Botanic Gardens. I have no idea. It's really close, but I'm going to point in the wrong direction. But anyway, somewhere really close to us, a few hundred metres that way. There is one of the longest running rain gauges opened in 1885. And what I did in this graph here is I took all the daily data from 1885 and I just plotted out a histogram. So this yellowy brown colour is the histogram, and you can see that for about 32,000 days out of the last 100 years, there's been 1 millimetre or less of rainfall falling in Sydney. That's the most likely amount of rainfall. And the blue line is the cumulative frequency, so it goes up and up and up. So probably 99% of all days since 1885, there's been 40 millimetres of rainfall or less in Sydney. Now, last weekend, I think in Sydney you had 29 millimetres-ish or something. On the Central Coast, we had 59, I think, so we had a big wet. But if you ignore that, I went back through the last year for the Bureau and actually had looked and had a look and said the last time there was 5 millimetres of rain was only 2 days before I looked. 10 millimetres of rain the last time was 18 days prior. 20 mils was 72 days before. 30 mils was 116 days, and so on down. And the last time there was 100 millimetres of rain in a day was a year and a third back in the past. So these are relatively rare. These are quite common. So the question is, at which level do you think you get groundwater recharge? Is 5 millimetres going to be enough rainfall in a day to get water to percolate into the groundwater? Or are we down here in the sort of higher values? We don't know. And so this is where I'm going to use the caves to go and find out. So have a think in your head, I'm not going to ask. But there'll be some data coming through now. So the data I'm presenting is mostly unpublished. One of the sites has been published, and most of these sites is unpublished. We're working on publishing them at the moment. The reason why it's not published and why it's taken 10 years is because there's so infrequent observations of potential recharge in these caves in some regions. It is phenomenally rare, and to get a large enough statistical data set to actually do something that's publishable, in fact, to wait this length of time. And it's been so long, I've actually gone grey. So this was maybe 7 or 8 years ago, with me downloading some loggers, and I'm definitely not that hair colour anymore. And so on the left-hand side, we have some pictures of me downloading loggers at Urangarilli Caves, lovely caves house there if you've never visited in recent years, nicely refurbished. The middle photograph is from the Wombian Caves, which has just reopened after 2 years of the flood damage after the fires, and there's a brand new visitor centre and a brand new fully accessible pathway down to the arch there, and that's spectacular. And on the right hand side there's some pictures from Wellington Caves, and we're using these acoustic loggers. So all this is a pressure transducer. It's a drum. There's a pressure transducer on the top under the cover. I should point. So there's the water drops on there, and you can tap the top and the light flashes on the side of this one. And so it's recording every single drop of water that's falling onto that logger. And there's a standard 3.6 volt battery in there, which will last about 4 years, and you can program them up, and they're completely waterproof. They survive floods. We know that because they've been flooded several times at Wellington Caves. You can see the flood line up here. The loggers are beneath it, so they've floated away a few times. So they're completely robust. They last for a long time. They were designed for people that were interested in taking stalagmites from caves to look at past climates and past environments, which is the other thing that I do. And they're designed to be sold like one-off. So an academic will buy one of these things, put it on their dream stalagmite that they want to go and sample for a paleo climate, past climate, and then they'll get the data, and then if it works, they'll ask for permission to sample. And then we wrote to the company and said, we want 100. And they went, oh, that's our biggest order ever. And then we asked for another 100. And we use them for groundwater, not for stalagmites. So we put them in all sorts of places, and that's the data I'm going to show you. And we'll start off with some of the published data, and then we'll end up with some of the latest things. And so the slides here, these are the results, and I guess the main point that I want to talk about this evening. There's going to be a repetitive sort of theme now for the different sites, so you better find your way around. Same sort of slide sequence from multiple sites. So we're going to start in the Garago country, which is the New South Wales Snowy Mountains, and South Glory Cave. So this is the Glory Arch, which is a really distinctive feature in the landscape, and it's increasingly recognised that the First Nations people were using this site because you see this in the landscape. It was an obvious feature, but we don't. What the actual use is lost. And the cave I'm working in here is this feature here, South Glory Cave, and these are some of the stalagmites and stalactites you can see in the cave, and you just see a logger sitting there on one of the water flows, and maybe you can just see a logger sitting there on one of the drips coming in here. So in terms of the hydrogeology, the water table's down here. This is the Urangarilli River. The cave's up here, and the water's percolating in from the hillside above the cave, and there's no other water source. So this is really good for understanding groundwater recharge. We know that this is the catchment, and we know that the creeks either side drain into the river systems. This is going to be representative of groundwater. And this is some UNSW students on the right-hand side who have volunteered to help. So this is quite an alpine site then. So the mean annual temperature is 11 degrees centigrade. The total annual rainfall, 1,260 millimetres. The pan evaporation, so if you just put a water pan out there and let it evaporate for a year, it would evaporate 1,492 millimetres. So evaporation is higher than the rainfall amount. This is true for the whole of Australia. It's even true on this alpine location. So although it's a temperate climate, with a warm summer, by technical classification, it's water limited, and all the sites I'm going to present to you are water limited. So this is sort of the workflow of what we do. So this is the data from this site. So I'll talk you through this one more slowly because it's the first one. So we're going to start in April 2013, and we're going to go through 6 years of hydrology data, and there's lots of these time series here in the bottom time series, which are all from these drip loggers. Each one of these colours is a different one of these loggers. It's come from another one of these loggers that's going around the room at the moment, each individual. And we're measuring, in this case, how much water is dripping onto them in a 15-minute period. That's just the time period that I set the loggers up for. Above that, we have the important climate information that we need to understand groundwater recharge. So we have, on the top, we have daily rainfall from the Bureau of Meteorology. Ignore the red dots for now. The black data there is just the daily rainfall. So you can see it ranges between about 0 and 40 millimetres per day in this region. And this is the daily evapotranspiration. This is from a model, because it's very hard to measure, from the Bureau of Meteorology. And it shows a very clear seasonal cycle, where it would have typically 2 to 4 millimetres of evaporation per day in summer, and then maybe 1 millimetre of evaporation a day in winter, and it goes through a nice clear seasonal cycle. So you can imagine if it rains and you have 5 or 10 millimetres of rain in summer, and it doesn't rain for a week, and you have 3 or 4 millimetres of evaporation per day, that rain's not going to be useful. It's not going to get to the groundwater system. It might help the plants in the soil. Whereas in winter, you might have 10 or 20 millimetres of rain, only 1 millimetre of evapotranspiration a day. So if you have enough rainfall events, maybe you get more recharge. So what we did then was go through every single peak on this drip logger series. Every time there was a potential recharge event, we lined it up with the rainfall. And that's what these red dots are. Every time there's a red dot is where there's a recharge event observed in the caves. So going back to that first question that I pitched, which is how much rainfall do you think is needed? Here we start to get some idea of how much rainfall is needed to generate groundwater recharge. The lowest red dot is probably around about 10 millimetres, 5 to 10 millimetres in a day, and most of them are between 10 and 40 millimetres. So we're starting to get a feel that to get the water through the soil and into the subsurface, we're going to need a figure at this site of more than 5 or 10 millimetres a day. And this is the coolest site I'm going to show you. The other sites are going to get increasingly arid and water limited. So even at this alpine site, which is relatively cool, it seems you're not going to get a huge number of recharge events. So to summarise it, so over that 6-year period, I counted them up, there's 100 recharge events in that series. So there's 16 times a year, there's enough rainfall at Urangabili Caves to generate recharge. This is a site which has an aridity index, which is the ratio of the precipitation to the evaporation, of 0.84. So there's more evaporation than precipitation. And when you look at the rainfall that's occurred before each one of those recharge events that's observed, and I've taken the 7-day rainfall here because it actually takes a day or two for the water to get into the cave, so you'll never be quite sure what the rainfall event will be. 55 millimetres of rain are needed over a week at this site to generate groundwater recharge. And you need less rainfall in winter because there's less evapotranspiration. So 31 millimetres is needed over 7 days in July, and more than 65 millimetres is needed over 7 days in January. That's our coolest, least water limited site. And it's just one location, one cave. So the next thing to do then is to duplicate that. So we're now moving into the unpublished data world already. So there's another cave at the same site. It's a former tourist cave called Harry Wood Cave. This is one of the caves that Pauline Treble had been monitoring from ANSTO since her days of her PhD, and she invited me to go and carry on the monitoring. So we put in some loggers. This is the work originally published by a lady called Monica Markowska for her honours research when she came to join us at UNSW. She's now a United Kingdom Royal Society Fellow, a highly prestigious 7-year fellow, just starting in the UK to go and look at stalagmite records of arid climates across the globe and the expansion and contraction of deserts using caves in arid regions of the globe. And so this is where she started before heading off in this prestigious career. And this is next door to the other cave we've just shown. So here's another time series. This is a bit more up to date because we're still collecting this data, and I say it isn't published. So Monica's honours thesis which he published is just here, this little bit right down here, in 2011. And now we have 13 years of data. I've not shown every single logger because it gets too messy. So now I've just given you like an average for the whole cave. But trust me, there's 30 or 40 loggers hiding behind here. You start to see a few data gaps coming in here. So here's COVID, for example, a classic problem for a lot of field science. We could not get to do a download in time. Also happened at the same time period was the fires, and so I forget which fire, the name of the fire that came down through Urangabili, but the fires came through in late 2019 as well. So there was a fire event that went over the cave. And an interesting, another unknown research question is to understand the impacts of fire on groundwater recharge. Anyway, so far we have 175 recharge events over about 13 years. This cave has a faster response to rainfall, so we actually see the response within 48 hours, and that's because it's a shallower cave, so there's a much more direct connection. And there's no seasonality in rainfall in Urangabili at the moment. But if you look at the data, we see many more recharge events in the winter months. So if you're in June, July, August, there's many more recharge events than in late summer, February, March time. And that, again, is the effect of evapotranspiration. The soils are going to be really dry after a long, hot summer. And so I won't say it's almost impossible. It's very hard to get groundwater recharge in those months compared to in winter. So we see this seasonality coming out in recharge events, which you can't see using these other techniques. You can't use isotopes or chloride mass balance because they're not at this time scale. So this is our replication study. I'm presenting this for the first time at an academic conference next month at the American Geophysical Union Congress in San Francisco. So they're going to see this. You're the first people before that. 175 recharge events over 11 years. So that's 16 a year. It's exactly the same. That's remarkably consistent. I don't believe that's going to stay as good as that. The 3-day sun precipitation, because we can now look at a sort of window, is 33.5 millimetres. So 33.5 millimetres of rain over 3 days to get recharge. And it's less likely in summer and autumn because you actually need to have the soil saturated to actually then get the recharge to come through the soils, and that's not going to happen in late summer because the soils are bone dry. So let's go now to a different climate zone. We're going to go somewhere up the coast, and this is the collaboration with the Kempsey Speleological Society and Angadi country. So we're in the Upper Macleay, and here we have an annual temperature which is 18.7 degrees centigrade, annual rainfall of 1,200 millimetres, the modelled pan evaporation of 1879 millimetres. So there's almost 50% more evaporation than rainfall here, so that we lose a lot more evaporation. And the climate, again, is temperate. This is one of the caves. That's quite typical up here. So these are all in national parks. This is proper potholing, research caving. And the lower figure here is from the Lower Macleay. This is from a place called Yezeba. And this is perfect for groundwater recharge monitoring. There's springs at the bottom of the hill. This is the recharge zone on the top here. So only rainfall falling on the hill will actually get through to the caves. This photo was taken in 2019, just as the fires went through again. The fires didn't reach Yezeba in 2019, but you can see how the trees are looking really stressed at the end of the drought. All of this region has just been burnt out in the Willy fire that's just been put under control. And we've yet to get back up in there and see how that's affected things. So that's another area of research for us to go and look at. So this data was published. I should say there's a reference there in 2020, but of course the data is still coming in. So the published data sort of finishes, I think, round about here in this graph. So here we have a whole bunch of loggers, different colours for different loggers, different cave sites, and now we have multiple caves. This is basically anywhere we found a suitable site for with the caving club, they put loggers in caves. They wanted to get a full spatial coverage of the site. We have about 7 years of data. We have 40 recharge events alone in the recent La Nina climate phase over the last 3 years. So when we published the paper, we basically got to 32 recharge events, and I said, yes, that's right, we've got enough data here for a paper, we can publish this, and then we did. And now we kept on getting the data, and we've doubled the number of recharge events since publishing that, and so we now have to go and reconsider that again. Now, this site, most recharge events occur in summer, and we didn't know that before because we don't have any way of getting recharge measurements out of an individual event basis. So you can see here, over the whole time period, the majority of the recharge events occur January, February, March, and December. So we're coming into the recharge season now, and that's because we're up the coast. Here we are, we're up the coast. So we're getting into the part of the country now where the monsoonal trough is getting close and the trade wind influence is coming in summer. So those humid easterlies, you can get some ridiculously high rainfall events, high amounts in this part of New South Wales. So 100 millimetres, 200 millimetres of rain a day is not uncommon upon these very large rain dumps. So, so this is the opposite. So even though the evapotranspiration is highest in January, February, March, there's so much more rainfall in that season that we do actually get recharge. And conversely, in winter, we're actually getting much lower rainfall, much lower number of recharge events because the rainfall is much lower. It's much more stable climate. So we're starting to see now in these data sets that we can actually start to relate things to climate. And that's an even bigger unknown. We don't know how much rainfall is needed to generate groundwater recharge. We definitely don't know how groundwater recharge relates to climate phenomena such as El Nino, Southern Oscillation, the Indian Ocean Dipole, or something that's called the Southern Annular Mode, which is the northern-southern progression of the westerly circulation through Australia. But by using this sort of data set, which is unique, we can start to look at the effects of climate modes and try to investigate how future climate change may also impact groundwater recharge. So for the Macleay cast then, we have 73 recharge events over 7.5 years. Only 10 recharge events per year at this site, which is more water limited. The aridity index here, 0.65, so there's much less rainfall compared to evapotranspiration. And here the median 7-day rainfall that's required is 76.2 millimetres, so higher than the other sites. And we have more recharge events in the summer wet season compared to the winter. So it's different from the Snowy Mountain site, and we didn't know that either. The final site of the three, I'm going in the increasing aridity. So now we're heading off into observatory country, and this is central west New South Wales, Wellington Caves, operated by Dubbo Regional Council. So this is the Mitchell Highway, heading towards Orange in that direction, or Wellington that way, Caves Road and the Caves Complex. And inside here we have a whole bunch of infrastructure in the caves, including all these loggers situated at the lowest possible level in one of the tourist caves, which is Cathedral Cave. So now we're getting warmer, 17.2 degrees centigrade, drier, only 620 millimetres, much more evaporation, so potentially you'd have 2,231 millimetres of rain, of evaporation if you had a pan out there. Of course it never happens because only 600 millimetres of rain a year, but potentially that's what you could have. So it's very hot, very dry. And we haven't published this data set because as it's getting hotter and drier, we're not getting the recharge events. So we've got 13 years of monitoring and ongoing, and this is another one of these summary graphs. It's now split onto 2 time series because the time series is getting so long. So we started in 2010, and we probably only got this site instrumented because we started in 2010, which was a La Nina year, and it was wet and there was floods across lots of inland New South Wales, which meant the water was percolating down, the groundwater was recharging, and the cave was wet, so we could actually set this up. And in hindsight, we got lucky, and the cave actually flooded, and we actually had to go and reset the loggers. Because after that, there were almost no recharge events. So from 2010 to 2016, we had a whole bunch of recharge events in that La Nina type phase. Almost none, and then we go back into 2016, another little cluster. This is the last drought where the 3 billion was spent trying to put the bores in, and there was drastic water shortages in the central west, water cartage everywhere, and then finally we started to get the first recharge events coming through in 2020, and then another huge cluster of events as we went through the recent wet period in the last La Nina and negative Indian Ocean Dipole phase. And we've got to 32, so we've probably almost got enough for a publishable data set. So we're thinking about publishing this, and I guess we're going to have to because we're going into a dry, so nothing else is going to happen now for a few years. So we have 32 recharge events, 14 alone were in the 3-year period of the triple dip La Nina. Most of the recharge events occur in winter and spring, and less rainfall is needed in those months. So you can see in this table, here's the months of the year. In July, August, September, there's 6 recharge events in total in all the Julys over that time period, 7 in the September, and the minimum rainfall needed over 7 days is only 20 millimetres. However, in February, March, April, February and April, there's not been a recharge event over 13 years. There's not been enough rainfall that's generated recharge. There's been a couple in March, one in January, and the rainfall amount's been over 100 millimetres over that 7-day period. And if you think about how much rainfall is needed, we just had 29 millimetres in Sydney for the weather system we just had, which was a fairly stationary frontal system with a trough involved. In Central Coast, we had 69. So you need these specific rainfall conditions. You can't just have a thunderstorm or a front coming through. You need some of these things that involve an East Coast low or a high-level trough or a cut-off low-pressure system converging with a trough to get something that's stationary, that lasts for 50 to 100 millimetres of rain in a day to get these recharge events to occur. These are not day-to-day weather phenomena. So to get recharge is increasingly not common in these sites, highly dependent on climate drivers, and also dependent on very specific weather systems as well. So in Wellington, we have 32 recharge events over 13 years. We're down to 2.5 on average per year. The aridity index now is really low, 2.8. We need 52 millimetres of rainfall on average, but only 18 in winter and over 100 in summer. And if you plot all that data up onto a graph, which we just started to do for the first time, so this is the aridity index. So this is Wellington, really arid. This is the Snowy Mountains, still water limit, but not so arid. And this is the number of recharge events per year. You can start to see there's a trend there. So as you get less arid and more water, you increase the number of recharge events. And then I've also shown on here the number of events depending on climate. So wet is blue and dry climate is red. So you'll see you can go from 22 recharge events in the Snowy Mountains in a La Nina year, or a negative Indonesian dipole, which is wet, down to maybe 10 in a dry climate phase. And you see that across all the climate sites as well. And that fits into what we understand about the rainfall for these different climate phenomena. So on the lower left-hand side, we have the rainfall 10 percentiles, the deciles here, for the 12 most significant La Nina years on record. And so you can see here, this is January to March, you can see it's really wet along the coast. And after La Nina year, this is the region where we have the Maclay cast here, and we do get more recharge events because of that. So we're starting to synthesize some fundamental understandings. 20 to 100 millimetres of rainfall is needed over several days to get groundwater recharge. Climate is important, as well as aridity, and we don't know what's going to happen with climate change, but because we start to understand these things, we can then start to model that, which is one of our areas of future research. But what we're doing now, I'm going to finish on 2 or 3 slides of the current project with a request. So if you know any interesting underground spaces anywhere in the country, I'm always interested to find out more about them. So we have this National Groundwater Recharge Observing System. The team is here. We have different leads. So Margaret Shannafeld, for example, is the lead for South Australian sites. Wendy Timms is in charge of Victorian sites and has also taken over Tasmania, like the Victorians do. I'm New South Wales lead, and I'm also moving up through into Queensland. We have Martin Anderson, who's a link with something called the Australian Critical Zone Observatory. And we have a social scientist and human geography and caver, Marilu Milo-Zurita, who is taking our data and our interactions with the community to actually help understand how groundwater knowledges are transferred to different communities. And the whole premise is that we're going to take any underground space, tunnels, mines, whatever's available, and we're going to use this same approach to go and look at groundwater recharge in rock types that aren't caves, that aren't limestone, because then that means we can answer a whole bunch of other questions about how important is the geology. Is our data unique to limestone rock types? Is it comparable to other locations? So this is our preliminary data set. We've got many more sites than this, and you can't see the locations because I've thrown on top of that a Köppen climate map showing different climate zones. But we have sites going through into Narracor Caves, for example, in Adelaide Hills, some of the old mines there, loads of gold mines, heritage, active and tourist mines across Victoria. We have a mountain bike tunnel down in Tasmania, just been joined the network. We got as far as Rockhampton and Capricorn Caves, and a whole bunch of sites across New South Wales that are mostly karst sites. And I should say that if you want to read more, there is a preprint and a website, and the data is all publicly available as part of this database. So here's some pictures. Here's two of the prettier pictures from two of the mine sites in Victoria to show that where the loggers are just situated, catching percolation water as it comes through. And the sort of data that we're getting, which is very similar to the data we're getting from the cave. So on the left-hand side, we are working with the national parks and traditional owners and in the Rowan country of the Viaduct Lava Cave, which links down, it's above the Bush Bin World Heritage Site for the eel traps. So we're linking into the groundwater recharge that feeds into that river system. And here's just a snapshot of data from October last year. And you can see a whole bunch of recharge events coming in, 1, 2, 3, 4, 5. Here's the rainfall that occurred beforehand. Here's how much rain that occurred in the previous 48 hours, sorry. And you can see there's about 10 to 25 millimetres of rain that's needed to generate recharge events. And this is in basalt, completely different geology, Quaternary age, and we're seeing a very similar sort of set of recharge thresholds. Over in the central west New South Wales, we actually have gone into the phosphate mine, which is in Devonian marble next to the tourist caves. And again, here's some data from 2022 with 3 recharge events. And again, some more data here for the 48-hour antecedent rainfall. And again, we see the same sort of thing. So we see between 20 and 40 millimetres of rainfall needed over 48 hours. So back to the question of, was there enough rainfall in last weekend to generate groundwater recharge in Sydney? 29 millimetres, probably not, no. Central Coast, probably yes. I think we probably did. But it's right in that threshold, but probably 29 millimetres. I didn't travel down to Sydney that weekend, but I guess you would know, because if you were travelling around on the highways or the train lines and you started to see water coming out the fractures of the sandstone, then recharge will have occurred. I drove down from the Central Coast tonight, and okay, it's a few days after, but everything looked dry on the faces there, so I didn't see anything that was actually actively happening now. So I suspect it wasn't enough, and that was a pretty wet and horrible weekend. So that's how much rainfall we need to generate recharge in this part of Australia. So I'm going to conclude and to thank you for your time. So caves, tunnels and mines, I would propose, are observatories of the recharge groundwater, and it's important that we can do this at the time scale of individual rain events, because then we can link groundwater recharge to weather and to climate, and then to climate drivers, and then to climate change. And there aren't any other ways of doing this. In fractured rock geologies across Southeast Australia, they're the ones we've focused on, there are very few rainfall recharge events per year. 2 or 3 on average in the Central West for the limestone out there. Maybe 13 to 16 as you go into the alpine sites in the Snowy Mountains. But 2 to 3 recharge events in the Central West, that's nothing, and that's an area where there's dryland farming. That's where you're absolutely critical on. And that's because there's this threshold where you need between 10 and 100 millimetres of rain per rainfall event needed to actually generate that recharge, depending on the season. And that requires these very specific, normally stationary weather conditions. And a typical summer intensive thunderstorm like the ones we're going to experience probably over the next couple of days will not be enough. It will not generate recharge under any circumstance for any rock type. It's just not enough rain. And most importantly, I think we can start to identify the relationship between the number of recharge events and the aridity and the climate drivers for the first time, which means we can then start to use this data more usefully in helping manage our sustainable use of groundwater in this country and elsewhere in the world. I'm going to stop there, and thank you all for your time.
Thank you very much, Andy. I'm Liz Deane, and I'm the Secretary of the Program Committee, which looks after all these types of events. So I'm actually going to be the controller of questions. So who would like to go first? Please.
It makes sense to ask the question, does groundwater flow, and where does it flow to? Does it follow the river basins, or does it have their own destiny?
Yes, that's a very good question. So the groundwater will flow to the lowest topographic point, and in this part of Australia, it'll probably be the sea level. So you actually have all this groundwater as submarine estuaries that you don't see heading towards the base level there. So the rivers may be too high and perched above the groundwater and they're not involved. There may be lowland rivers that may then be a receptacle for groundwater. It really depends where you are in the landscape. If that answers the question. One of the interesting things about the Great Barrier Reef at the moment and the nutrient inputs into the ocean close to the Barrier Reef is that it's probably coming from groundwater. And there's all these submarine groundwater flows coming in. So we all grow blueberries and other commercial crops and add nutrients. And if you oversupply, everyone focuses on the river systems, but actually it's the groundwater system that's the bigger contribution, because that water is going to reach base level, and the base level there is going to be the oceans. And that's where it's going to then mix into the ocean water, which is, again, another hidden aspect of groundwater. So thank you for the question.
Something of a follow-up to that. With the floods that we had a couple of years ago, and there were enormous amounts of water just sitting there for weeks, how long does that water take to migrate through the system, and how productive is it in terms of sustaining the environment?
That's a good question. I don't think I can answer that one. I mean, it's a very good question. So the immediate floodwater, that's lost straight to the ocean and not useful. The approaches we're using here, it's really good at the timing of groundwater recharge, but doesn't give you the volume. So you don't know how much that water is actually going to be recharging there. So in terms of your stagnant water on the surface, is that because the water table's at that level, which it probably is, which means it's just ponded. As the water then goes down, how much of that water actually then percolates down and recharges? If there's 3 millimetres of evaporation per day, is it being lost by evaporation more quicker than it is going down? I mean, you can model it, and it'd be different for every site, and I don't think there's any one answer to your question. You might lose it all, you might get some.
I've been in caves where I've seen bushfires have had an effect. There's been charcoal in stripes on the within the cave. What effect do the bushfires have on the groundwater? Apart from staining, obviously the water's moving down with the charcoal.
Yes. Okay. So at the groundwater scale, I would say we don't know in terms of a groundwater volume what happens. There's almost no research out there. We had one study by chance, I didn't show tonight, from Wombian Caves, where we were monitoring a cave and we actually had an experimental fire for different projects, and so we could work out what happened before and after the fire. And it did seem that after the fire you needed much less rainfall to generate recharge into the cave, and that's probably because the soils have been damaged and we've lost a lot of the soil cover, so you get more direct ingress. In terms of sort of the geochemical impacts and the black coloration, what we're doing in a different project with colleagues at UNSW is we're detecting past fires in cave stalagmites from the chemical signature from the ash that's come from the surface, which is, I think, where your question comes from. And so we're looking at the soluble fraction of the ash. So the ash sits on the surface after the fire, and then there's some rainfall events after that, and the soluble fraction gets washed down into the cave, and then we can measure that it gets trapped in the stalagmites. And then it's a question outside my expertise area about how trees bioaccumulate metals. But what we tend to see is a predominance of nutrients. So we see lots of nitrogen, phosphorus, sulfur in the stalagmites related to where there's a fire, because I guess that's the greatest abundance in the
I appreciate that this question relates to volumes, whereas recharge is actually a flow rate. But where is the water that is not contributing to recharge? Is it in the atmosphere locally? Is it diluting the ocean locally, or has it moved geographically?
Yes, so some of it would have moved geographically. So if you have so much runoff, it'll go into the river systems and it'll run off to the ocean, so it'll be a plus to the ocean. But the biggest loss will be back to the atmosphere through evaporation or evapotranspiration. And that's the big unknown. So as recharge is occurring, or potential recharge is occurring, there's going to be an evaporation from the near surface, and then there's going to be transpiration from tree roots and plants from depth. And so the water's got to get past all those processes to actually get into the groundwater, if that answers your question.
But when we're having a groundwater drought, the missing water is not hanging overhead in the atmosphere, is it?
Well, it's going to be in water vapour in the atmosphere eventually. I mean, if it's evapotranspired, it will go back into the atmosphere. and then become part of the atmospheric circulation again. So yeah, it would go up into the atmosphere.
When you're in the cave system, clearly there's an atmosphere in there that has a certain amount of moisture content in it. Does the humidity impact how far into the cave you have to go with your sensors?
No,
Not relevant?
No, not at all. Because so we're measuring the water that percolates through. So no, it's controlled by the size of the fracture more than anything else. So once the fracture is wide enough, it comes in, and that's it.
Excuse me, yes, I'm from Canberra. Apologies for two local questions. Is recharge different from snow than from rain, given you're looking at the Alpine? And to what extent is Lake George an open-air cave, given that I don't think it's got runoff from rivers?
Yeah, I mean, Lake George is great, and I always make a point of looking at Lake George and using it every time I go to Canberra to talk to politicians or anything. I make the point that it's a surface weather gauge looking at groundwater. When the water comes up in Lake George, it's groundwater reaching the surface. When it goes down again. It's a rain gauge. Now the first question I saw, I've forgotten. Snow, yes. So the Urangabili site does have snow. So the snow will sit there, and then and then when it melts, you then get a higher volume over a shorter period of time. So that may change the recharge characteristics. So the answer is a maybe. So you get delayed recharge, but the water's still there, so it's just delayed.
Thanks, Andy. A quick question. I'm missing something here. In one of your early slides, you spoke about salt ratios in rainfall and groundwater, and you would work out how much was getting through and so on. I don't understand. I didn't think rainwater was salty. It's fresh water when it evaporates out of the ocean. The salt stays in the ocean. So where's the salt content in rainwater?
Yeah, no, there's a small amount in there.
Is there?
Yeah, just a small amount. So yeah. Especially think of the ocean source water as well. It'd be highly saline. So the water that's forming near the coast and the groundwater that's formed has actually got high metals that relate to salt. So sea spray, sodium.
That'd be true close to the ocean, but it wouldn't be true.
Yeah, it's very, very low, but it does accumulate all through time. So that's how we get the dryland salinity. So over time, we get the trees pumping out the water, the rain falling. There's some natural salts in the rock and that may contribute, but the rainfall is just sitting there and it's got a low amount of salt in it. So you work out the ratio of the rainfall salt contribution compared to the
fascinating. Thank you.
The groundwater, and you get this up concentration value. So yeah.
Interesting. Okay, thank you.
Well, thank you, Andy. Do you position each logger under a drip, and do you make any attempt to catch every drip in the cave? And how long do the batteries last?
Right. Well, the second one, 4 years is the batteries. Yeah. So upscaling. So this is the really good question. This is the link between how do you go from timing the recharge to the volume? Because what you want to do is measure every single drip, which is financially impossible and a huge time cost. So I had one researcher, a guy called Kashif Mahmood, who took on this challenge a few years ago. No one else has done it since, but I'm still looking for keen volunteers who used LiDAR and used cave LiDAR to actually map the cave. So we went to one cave, we had loggers there, went into the cave system and used LiDAR to map every single stalactite. Then he wrote the code to work out what sort of stalactite it was, whether it was a thin straw versus a big curtain, because we knew that the flow would be faster through the big curtains than the thin straw. So he characterised all the roof characteristics, and this is the total number of potential recharge sites. But the LiDAR couldn't see which ones were actually active. Some of these things are fossil. You can't see the drop of water. So we then had to go and use photogrammetry, actually take classic photographs, and then look for the reflection for the water beads and do another coding exercise to count the number with water on and the different types of stalactites and mesh them together, and then upscale all our data to go and get a recharge volume, and it sort of made sense, but the errors were huge, as like all recharge estimates. So it was a huge effort to show technically what's possible, and it was an interesting exercise, but far too hard. So if anyone's got a better idea of knowing, there must be an AI solution to this, I guess, coming, but
Okay, thank you.
That's right.
Thank you, everyone.
Well, in the interest of the announcement that we just heard that we're going to be evicted in 2 minutes, I'll thank Andy very much for another wonderful Clark lecture. And we hope that we can publish your lecture in the Society's Journal, Andy, to add to the lineage. So I'll ask our editor, who's not here tonight, to contact you. So with that, I close the meeting and invite you all to come up to the library bar on the roof. If you don't know where it is, just follow the rest of us. So thank you.